Hello, everybody. Welcome to week 7. We're getting there. Last week we talked about conjugacy, and last week really I suppose the content was mostly sort of conceptual. We were talking about the concept of conjugacy and the fact that the relation of conjugacy splits any group up into a disjoint union of conjugacy classes. I think the experience of students in this course for the last couple of years in the last week's content has been one of the most sort of technically challenging parts of the course. We're going to have our feet a little bit back more in the ground this week. We're going to be talking about permutations and about the meaning of conjugacy in the precise context of the symmetric groups, the groups of permutations. So one of the things we noted last week was that within the general linear groups, for example, the concept of conjugacy has a meaning that's familiar to us from linear algebra. Two elements of GLN or whatever, GL, general linear group of 2 by 2s, let's say over the real numbers, are conjugate to if and only if they're related to each other by the concept of similarity in linear algebra, which means that as linear transformations, they represent the same transformation, only with respect to different bases. So general linear groups are an example of somewhere where one can attach sort of a geometric meaning to the notion of conjugacy and sort of use that to recognize or interpret what it means for two elements to be conjugate to each other. Generally speaking, there isn't always in any group sort of a nice description like that, apart from the definition that sort of tells you whether two elements are conjugate to each other or not, or what it means for two elements to be conjugate. Another nice exception where you can actually say a little bit more and where you can actually give a sort of description of elements that are conjugate to each other is in the symmetric groups. So let's just recall that the symmetric group Sn is the group of all permutations of n objects. And it's typical, though not necessarily required, to label the n objects as by the first n positive integers 1 through n. Okay, so the symmetric group Sn is the set of all permutations of n distinct objects under the operation of composition of functions. Okay, and it's worth bearing in mind that although we're using the symbols 1 to 2 up to n to label our n objects that are being permuted, they're not really the first n integers. They're just labels that are used to describe our n objects. So like they don't have all the arithmetic and algebraic structure of the integers. They're just n things. Okay, and then just to recall what we mean by a permutation and what the composition operation is. So an element of S4 then is a permutation of the set whose elements are 1, 2, 3, 4. Okay, that means a function whose domain is 1, 2, 3, 4, which takes 1 to one of these 4 elements, 1, 2, 3, or 4, which takes 2 to a different one of the 3 remaining choices, 3 to one of the 2 remaining choices, and 4 to the last one. So so one can regard it as a sort of shuffle of the 4 elements, but if you think of it as a function, it means that we have a composition operation for functions. Okay? And as we know, if we want to consider, for example, the permutation in S4 that takes 1 to 1, 2 to 4, 3 to 2, and 4 to 3, a standard way to denote that or to tabulate that information is to write an array. It looks like a matrix, but it's not intended to be interpreted as a matrix, which just has 1, 2, 3, 4 in their usual order in the first row. And underneath each one is its image. So 1, 4, 2 to 4, 3 to 2, 4 to 3. So the function here takes the entries in the first row to the entries in the second row. Again, we can recognize those array type descriptions of permutations. Okay, so we're claimed that the set of all permutations of n objects is a group. Just to recall, I know we did this earlier in the course, but just to recall it in case anyone's forgotten. If you haven't forgotten, you can easily skip this bit. So suppose that we're in S5, which means we're talking about permutations of 5 objects labeled here 1, 2, 3, 4, 5. Here are 2 examples of permutations of the 5 objects. And we want to calculate the compositions. So just to do that, if we want to calculate, for example, the composition sigma after tau, we call it sigma tau, and this means tau first, then sigma. So we apply tau first, and then we apply sigma. So tau applies to each of the elements 1, 2, 3, 4, 5. And we can write down what it does to each of them. So here's tau being applied first. Tau takes 1, 2, 3, 4, 5 to 4, 3, 2, 4, 2, 3, 5, 1 in that order. So 4, 2, 3, 5, 1. And then we can apply sigma to each of these ones. And the result of that, well, we have to just read off from the array for sigma what sigma does to each element. Sigma takes 4 to 4 It takes 2 to 3. It takes 3 to 5. That's here, 3 to 5. Next, we've got 5. 5 goes to 1. And we've got 1 finally going to 2. So we can observe that overall, applying tau and then sigma takes the 5 in their original order to the order 4, 3, 5, 1, 2. So we can say that sigma tau is the permutation, if we sort of return our completed calculation in the format in which the problem was stated. Sigma tau takes 1, 2, 3, 4, 5 to 4, 3, 5, 1, 2 in that order. And as we can observe, as we expected, if you compose two permutations, you still get a permutation. So as we might expect, we get, again, all 5 of the potential images appearing there in the second row. If you wanted to calculate the same composition of the same two elements, but in the opposite order, we can, of course, do that as well. If we do tau sigma, I'm just going to write down the answer here and let you check that hopefully I've got it right. Tau sigma would be another permutation in S5. So again, it would be writable as something that has 1, 2, 3, 4, 5 in its first row. Again, we're composing the same pair of permutations, but this time we're talking about tau sigma. So tau after sigma, sigma first, then tau, and we can look at what happens to each element. If we start with 1, we're applying sigma first. Sigma takes 1 to 2, and then tau takes 2 to 2. So overall, applying sigma first and then tau takes 1 to 2. Sigma takes 2 to 3, and then tau takes 3 to 3. So overall, applying sigma first and then tau takes 2 to 3. Sigma takes 3 to 5, and then tau takes that 5 to 1. So overall, in the composition, 3 goes to 1. Sigma takes 4 to 4, and then tau takes 4 to 5. So overall, 4 goes to 5. And if we're right so far, the last one should be 4. Let's see. If sigma takes 5 to 1, and then tau takes 1 to 4. So sure enough, we do find that we get a permutation for tau after sigma. And we can, of course, note that sigma tau is not equal to tau sigma, which tells us immediately that S5 is not abelian. The composition operation for permutations is not a commutative operation. And that's just to recall how composition works for permutations. And I suppose I encourage you, if you haven't done this recently, to just practice it a little bit, make sure that you're comfortable with it, and also with the notation in this array format. Okay, this is not really the main theme today. What I really want to focus on is the so-called disjoint cycle description or representation of a permutation, because this is really of interest to group theorists, and particularly from the point of view of the meaning of conjugacy in symmetric groups, which I claim is something interesting. By the way, one thing I should have mentioned about symmetric groups is, the symmetric group of degree n is the group of all permutations of n objects. It's very easy. It's very tempting to kind of think about symmetric groups as meaning things like groups of symmetries of polygons. So just bear in mind it doesn't. The symmetric groups are the full groups of permutations. It's slightly confusing that we also have, meanwhile, groups of symmetries, which are not symmetric groups. So it's just a kind of a foible of the way that the language is used in the subject. Okay, here's a permutation in S14. So as you can see, S14 is the group of all permutations of the elements 1 through 14. They all appear in the second row somewhere, I hope. And another way to visualize this permutation, which turns out to be quite powerful in group theory, is instead of just looking at it as a list of 14 elements and their 14 images, look at what happens if you start at a particular element and repeatedly apply the permutation to it. So if you start at 1, because that's kind of the first one in the natural order, you could start anywhere, but let's start at 1. And look at what happens if you apply pi to 1. We find that 1 under pi goes to 11. Okay, fine. So I think, here you can think about pi as being, if you want, some kind of physical shuffle of 14 things. Imagine them being sort of lined up on the table, 14 cards numbered 1 to 14, and this permutation is going to shuffle them around. So it's going to take 1 to where 11 normally lives. Then look at what it does to 11. It takes 11 to 3. Look at what happens to 3. 3 goes to 8. Look what happens to 8. 8 goes to 14. And keep going. Okay, as we keep going with this process, we can observe that this process cannot possibly keep going forever. We only have a finite number of elements, so we're not going to get a sort of infinite list here. Eventually, it's going to have to have some repetition. 4 goes to 2. We haven't had a 2 yet. And when the repetition happens, you know, we could ask, I mean, could it happen, for example, that we could find, we haven't looked at what happens to 2 yet, but you know, could it be that 2 goes back to 8 over here? Well, it couldn't, because what we're dealing with is a permutation. And for a permutation, every element has to have a different image. So this sort of trail of arrows can't continue indefinitely. It's got to have some repetition in it somewhere, because we only have 14 elements. But when the first repetition arises, we might wonder, like, could it be like this? Could it be like this picture with the green arrow in it? Well, if it was, it would mean that 2 and 3 would both have the same image under this permutation, which is not possible for a permutation. Okay, so there's no way that the path can sort of start repeating itself through some kind of loop like that. It must be that eventually it repeats itself by looping back to the starting point 1. Okay, because everything else in the list except for 1 is already the image of something. And you can't be the image of more than 2 things under a permutation. So I'm just going to tidy this up again here. Sorry, that's the opposite. I'll erase some of that stuff. And we'll keep going. So at the moment we're at 2. 2 goes to 9. 9 goes to 6. And 6 goes back to 1. Okay, so that's what happens to this permutation. If you start at 1 and just keep applying the permutation, you get this particular list, not of all 14 elements, but of 9 of them. And those 9 get cycled around in this sort of circular pattern. And this kind of already tells us something about this permutation that wasn't visible from the array version, which is that this permutation, okay, yeah, it permutes all 14 things, but within that permutation of 14 things, it permutes these particular 9, namely 1, 11, 3, 8, 14, 4, 2, 9, 6. It permutes those 9 amongst themselves. And the way it does it is by just sort of cycling them around according to this picture. Okay, so this is not a full description of the permutation pi, but it's part of pi. And the key thing here to think about is pi is a permutation of all 14 things, but amongst the whole 14 things, this list of 9 of them is permuted amongst itself, meaning that everything in that list of 9 things is sent to somewhere in that list of 9 things. And the way it's done is by this cycle process. Okay, that does not account for all 14 of our elements. So let's keep going with this idea. And if we look at the elements that we don't already have, we've got 1, we've got 2, we've got 3, we've got 4. The first one we don't have is 5. So let's start again with 5. And look at what happens to 5 under the permutation. 5 goes to 5, it's fixed. It's a fixed point. That's a bit of language that's useful to have. 5 is a fixed point for this permutation. Okay, that's fine. So 5 kind of belongs to a cycle of length 1. This is a cycle of length 9, which is also written as a 9 cycle. It's got 9 elements in it. Okay, so now we've got 1, 2, 3, 4, 5. We've got 6. It's here. We don't have 7 yet. So if we start again with 7, which is the first one that hasn't appeared yet, look at what happens to 7 under pi. 7 goes to 12. 12 goes to 13. 13 goes to 10. And 10 goes back to 7. So we get this 4 cycle, or a cycle of length 4 if you prefer. And now everything has been included. All of our 14 elements are here somewhere in this picture. 9 of them are in the first cycle, 1 of them is in the second one, and 4 of them are in the third. And no single element appears in more than one of them. So what we can say is this permutation pi in S14, it permutes all 14 elements. The way that it does it is it permutes these first 9 of them amongst themselves. It fixes one point, which is only 5, and it permutes the other 4 by cycling them around amongst themselves. So it's got what they call a 9 cycle, it's got a fixed point, and it's got a 4 cycle. Okay, and every permutation can be broken up in exactly this way into a collection of separate cycles. And this is called the disjoint cycle representation of the permutation. Okay, so what disjoint means is that every one of the 14 elements appears in exactly one of the cycles. Okay, and this is a sort of typical thing with permutations, that they have a description of this form. We can observe here we've got 3 cycles. One of them is length 1, one is length 4, one is length 9. You could imagine a permutation of 14 things that has, like, let's say 3 4 cycles and 1 2 cycle. So the key point here about the 9, the 1, and the 4 is that they add up to 14, which is our total number of elements. Okay, so, and again, this tells us something about this particular permutation pi. Its cycle type is that it has a 9 cycle a fixed point, and a 4 cycle. You could have another permutation that has just a single 14 cycle. You could have one that has a 10 cycle and 4 fixed points. There are loads of different ways to write these permutations. And of course, this is not the only permutation of 14 things. It has a 9, a 1, and a 4. There are others, and those ones somehow resemble this one in a very particular way that might not be obvious if you were to look at the array type description. Okay, so that's an element of S14. Okay, so we don't generally draw those kind of pictures with arrows, although we could. We usually have a sort of slightly more compact notation for these things. So in that example, there were 9 distinct elements in the first sequence, the one that started at 1, and the permutation produced this cycle that started at 1, went through 9 elements and came back to 1. So just to mention, for the sake of notation, typically that particular cycle would be written in this way. Okay, and so it's an alternative notation. It's a more compact notation for cycles. So it's just written in text as a list. There's no punctuation. It just goes 1 and then the image of 1, then the image of that, and so on. And then when it's ready to loop back to 1, you just close the brackets here, and that's read as the permutation that takes 1 to 11 to 3 to 8 to 14 to 4 to 2 to 9 to 6 and back to 1. Okay, so this is nothing but notation. There's no sort of new concepts in it, but it's a notation for writing a cycle. One thing that is worth bearing in mind is that this particular thing, as it's written, this is considered in the context of this example to be an element of S14, even though all that we have here is a description of what happens to 9 particular elements that get cycled around. So our understanding of what this thing is it's the element of S14 that cycles these 9 elements around according to the picture, according to the description, and leaves the other 5 elements fixed. Okay, so this is not pi, but this is the part of pi that cycles around those first 9 elements. And we think of this thing as it's written as being the element of S14 that cycles these ones around, the ones that are listed, and leaves the rest fixed. Okay. The set consisting of those 9 elements is called an orbit of the permutation pi, and it's the orbit to which, for example, the element 1 belongs, or to which the element 8 belongs. This could be referred to as the orbit of 1, or the orbit of 11, or the orbit of 3, or so on. What's meant by orbit is that if you just apply the permutation pi to this particular set of elements, the pi doesn't move any of these elements outside the set. It operates as a permutation upon that set within its pure operation. Okay, and also that there's some power of pi that takes each one of these elements to any other one. So pi takes 1 to 11, pi composed with pi would take 1 to 3, and so on. Okay. For the permutation pi, there are 2 more cycles. There's the one consisting just of the fixed point 5, and there's the one of length 4, consisting of 7, 12, 13, 10, and permuting them around in that order. So, and again, in this situation, each of those would be considered to be an element by itself as 14. This first one is the element that fixes 5. It also fixes everything else, so it's actually the identity element of S14. The second one is the element that takes 7 to 12, 12 to 13, 13 to 10, 10 back to 7, and leaves everything else alone, fixes it. So it's still an element of S14. The reason for emphasizing that is because we now write pi as a product of disjoint cycles. And here product means product as in composition in the symmetric group S14. We're saying that pi is the permutation that can be obtained by first cycling around 7 to 12, 12 to 13, 13 to 10, 10 back to 7, and then cycling 1 to 11, 11 to 3, and so on, back around to 1. Okay. So if you do both of these cycles, you've basically affected the permutation pi. That's what you've done. Okay. It breaks up into these 2 pieces, one of which acts on 7, 12, 13, 10. The other acts on these 9 elements. The 2 of them are independent of each other because they operate in different sets of elements that have no intersection. Okay. So the 2 of them literally commute with each other in the group. You might be wondering, where's the 5 gone? And the convention is, when you're writing a product of disjoint cycles like this, if there are some fixed points, you usually don't really write them. And if they're not written there, they're assumed to be fixed points. And you can put it in if you want to, so it's absolutely fine. But typically people leave out fixed points when they're describing permutations as products of disjoint cycles. So disjoint means that sets of elements that are moved by each part are separate from each other. And product means composition. Okay, so, and the key thing about these disjoint cycles is, I think of it here again as, think of it as 14 cards spread out along the table. If you were to implement this permutation pi on your list of 14 cards, if you were to do it using the array description that we started with, you can do that absolutely fine, no problem. You just move every card to its new location. But an alternative way to do it would be to take the cycle description and just take the cards numbers 7, 12, 13, 10, and the cards 1, 11, 3, 8, etc. Those two collections of cards separately, cycle each of them amongst themselves. And if you did that, it wouldn't matter in which order you did the two separate cycling parts because they don't interact. They involve completely separate sets of elements. Okay, so these permutations, which are disjoint cycles, they actually commute with each other within the group. Okay, that's the content essentially, I think, of the next slide. So remarks on this: every permutation can be written as a composition of disjoint cycles or a product. As I mentioned, conventionally, you don't bother including the fixed points, but you can if you want. Okay. Disjoint cycles, although they're written in this sort of terse notation with just the list of numbers and the brackets around it, they're considered to be permutations in the relevant symmetric group. In this case, it's S14. Okay. And what I mean by that is, although only a certain number of elements are written, the ones that are written down are assumed to be cycled around, and the ones which don't appear are assumed to be fixed points. And the reason why we need to have that conception is so that we can compose these cycles as elements of S14 or whatever Sn it is. Okay. Final remark: the written description of a permutation as a product of cycles is unique of disjoint cycles, except for two things. You can change the order in which the separate cycles are written because they're commute with each other. Okay, and within each cycle, what matters with the cycle is not which element comes first, but just the cyclic order. So the permutation that takes 1 to 2, 2 to 3, 3 to 4, and 4 back to 1 is of course the same as the one that takes 3 to 4, 4 to 1, 1 to 2, and 2 back to 3. So you can change the way that a particular cycle is written by just changing its first entry, as long as you keep the cyclic order the same, and you can interchange the order in which the disjoint cycles are written. But apart from that, the description is unique. Okay, so you can recognize fairly quickly usually if two disjoint cycle descriptions represent the same permutation. Okay, there's one other thing I wanted to mention in this section, and then I will stop talking, and that's just the order of an element in a symmetric group. So just to remind ourselves of the concept of the order of an element in a group, remember that if we're in any old group G and we take some element of G, called little g, the order of that element is the number of elements in the cyclic group that it generates. So it's the number of distinct powers that that element and its inverse have in the group along with the identity. So if that cyclic subgroup that the element generates is finite, which will always happen if the whole group is finite, then the order of the element is the least k, for which when you compose the element with itself k times, you get the identity. Okay, so basically if you are thinking about the order of an element, you're asking yourself, if I compose this element with itself repeatedly, how many times do I have to do it to get the identity element? Okay, so a remark about elements of symmetric groups is that their orders are quite easy to work out if you know about the disjoint cycle representation. If you're trying to do it at the level of the array, not easy at all. If you ask yourself, in S8, what's the order of that element? So that means if you take 8 cards, numbered 1 to 8, order them at the table 1 to 8, move the card in position 1 to position 4, move the card in position 2 to position 5, so on. How many times do you have to do that to get all the cards back where they started? That's the question. And if you're going to actually do this in a practical way by starting with 8 actual cards, it's probably going to take a while to keep doing this, and you won't really get any clues along the way as to how near you are to the end. But if you know about the disjoint cycle description of a permutation, then it's actually quite easy to answer this question. So first of all, to note, if you're given a permutation in its array type description, and you want to write down the disjoint cycle description, it's quite easy. It's quite easy, like everything, once you know how to do it, but it is fairly quick. So just decide where you're going to start, and the convention is to start at 1 because it's an easy way to keep track of where you are. You don't have to. If you start at 1, then you can say, okay, well, 1 goes to, if I start with 1, look at what happens to, I'll start writing my cycle that starts at 1, 1 goes to 4, then look at what happens to 4, 4 goes to 8, keep filling up this list until you get back to 1. When I look at 8, 8 goes back to 1, so I close off the first bracket there. What have I not had yet? I've had 1, I haven't had 2 yet. So I start the next one at 2. What happens to 2? 2 goes to 5. Go to 5, 5 goes back to 2, so I close the bracket. The first thing we haven't had yet is 3. 3 goes to 7. 7 goes back to 3, so we get another pair, another cycle of length 2. The first thing we don't have yet is 6. 6 is a fixed point, so you can either leave it in or leave it out. If you want to include a cycle here for 6, you can. If you leave it out, it's assumed that it means that 6 is a fixed point. Okay, so there's the disjoint cycle description of pi. Okay, now we can ask ourselves, this means what pi is doing is it's cycling around 1 to 4 to 8, like this. It's swapping 2 and 5. And it's swapping 3 and 7. Okay, not very legible, but luckily it's written there multiple times. So that's what a pi looks like. It also is taking the element 6 and sending it to itself if you want to include that. So we have to ask ourselves, how many times would we have to apply pi to get everything back where it started? So to send 1 to 1, 2 to 2, and so on. And you can observe that if you apply pi once to the 3 cycle here, then 1 is moving to 4, 4 to 8, and 8 to 1. If you apply pi twice, 1 is going to go to 8, 8 to 4, and 4 to 1. But if you apply pi 3 times, then you're going to go take 1 to 1, 2, 3 to itself, 4 and 8 also to themselves. So if you want to apply pi a number of times so that everything goes to itself under this repeated application of pi, in order for the elements that are in this 3 cycle, 1, 4, and 8, to be mapped to themselves, the number of times you apply pi must be a multiple of 3. Okay, so the order of pi must be a multiple of 3, otherwise the relevant power of pi doesn't fix the 3 elements 1, 4, and 8. But we also have to look at the other cycles. Okay? Every repetition of pi fixes 6, so that doesn't really enter the picture. For 2 and 5, if we apply pi once, 2 goes to 5 and 5 to 2. If we apply pi a second time, we've sent 2 and 5 back to themselves. If we do it a third time, then we're swapping them again. So an odd number of applications of pi swaps 2 and 5. An even number of applications of pi wraps 2 to 2 and 5 to 5. And exactly the same for 3 and 7, the other 2 cycle there. So if we want a power of pi that sends everything to itself, that power must be a multiple of 3 in order to send the 3 elements in the 3 cycle to themselves. And it must be a multiple of 2 in order to send each of the 4 elements in the two cycles to themselves. That's 2, 5, 3, and 7. So we need the order of pi must be a multiple of 3, and it must be a multiple of 2. And provided that k is a multiple of both 2 and 3, pi to the k will take every element here to itself. So what we need is the least common multiple of 2 and 3, which is 6. So we can say that if you do pi 6 times, everything is mapped to itself. That's the smallest positive integer with that property. And 6 is the order of pi as an element of S8. An important point to note here, when you're thinking about this, and you kind of almost automate the process in your head, it's very easy accidentally to, instead of calculating the least common multiple of the cycle lengths, 3, 2, and 2, to take the product of them, which would give you 12 in this case, which would be wrong. So what you want is the least common multiple of the cycle lengths here, which are 3, 2, 2, and 1 for the fixed point. Again, the least common multiple of 3, 2, and 2 is 6. If it was 3, 2, and 5, it would be 30. Okay, so the order of a permutation is the least common multiple of the cycle lengths in its description as a product of disjoint cycles. And that's another sort of key reason to be interested in the expression for a permutation as a product of disjoint cycles. It gives us a sort of a description somehow of its geometry, how it breaks up the set into different pieces and how it cycles them around. And from that, we can easily calculate, for example, its order, if that was something that you wanted to do. Okay, that's essentially just sort of rehash of some features of the algebra of permutations. You may have already known everything that was in this lecture. If so, hopefully it still helps as a way to remind yourself. If not, you can feel free to skip it if you already knew everything that was there. The next installment, what we will do is have a look at the relationship between the cycle representation and the concept of conjugacy in symmetric groups. And that's quite an interesting thing from the group theorist's point of view. Okay, thanks everybody. We don't have a challenge connected to this particular video. We will have one in the second one. So there's just one weekly challenge for this week, and that's coming up shortly. Thank you very much. See you soon.